Okay, so now we're going to briefly go over an introduction to fluid mechanics. And so, first thing we need to define is what is fluid mechanics. And fluid mechanics is the study of fluids, and we'll define what a fluid is later on. You guys have an intuitive feel for what a fluid is, so there will be nothing earth-shattering with the definition of it when I do it. But fluid mechanics is the study of fluids at rest or in motion, and when they're in motion is when they are most interesting. And so we will go over the after chapter 2, we will go into chapter 3, which will be on fluid statics. And then we will go into fluid dynamics after that. And so why do we bother studying fluid mechanics? Well, fluid mechanics is used to design many things. Many things. For example, it could be airplanes. Some of you are aerospace engineers, so that's a very typical thing. Rockets, pumps, it can be used to understand flooding. It can be used to design pipe and sewer networks. Which doesn't sound like the most fun thing in the world to work on, but it is crucially important for everyday life. Tsunamis. It's used by astrophysicists to study phenomena like supernovas. So fluid mechanics is a very, very broad field, and so just show some GIFs below. So this here is a GIF of how you'd use a wind tunnel to study the flow over, in this case, a Lamborghini, where you might want to design the car to not only look good, but to minimize drag. And what you'll find when we go over external flows, that a huge portion of the drag of a car is not on the portion in front here, but instead the drag is caused by a region of low pressure that occurs behind the car. And this region here is called a separation bubble. And you'll find that there's a large portion of drag is caused by that separation bubble. Or it can be used to optimize wind farms. So here's a computational fluid dynamics simulation of an array of wind farms. So here we have a gridded array of wind turbines, and they're studying how the flow among various wind turbines affects one another. And we will go over what these white lines are here in the next lecture, and those are called timelines. And I'll let it loop over again. And what they're doing is from this point here, they are releasing a bunch of particles and then following them in the flow to basically understand how the fluid moves. And what they basically learned from this is that in the channels that are along a line of wind turbines, the particles are basically held back, as they're basically way back here or way back here. But in the channels between the wind turbines, there is a lot more flow. And so they use studies like this to basically optimize the placement of wind turbines. And in fact, a more optimal placement is not this regular array of grids, but it's to actually stagger them. And then you extract more power out of the wind. But the basic concepts to understand these things you'll learn in this class. And there are governments and militaries that use computational fluid dynamics to understand blasts. This was a numerical simulation of the recent Beirut explosion, and they just used to understand where the pressure was higher, how the blast propagated, and sort of things like this. And there are a lot of municipalities that basically do these sorts of exercises to understand how blasts propagate in their city, or in the case of a terrorist chemical attack, They basically study how the chemical agent would basically flow between the buildings and things like that, so that if there is a chemical attack, the city knows how to allocate resources. But the basics behind this blast physics here that you see propagating outwards, the basics you will start to learn in this fluid mechanics class. And so shock physics, blast waves, things like that are also a subset of fluid mechanics. And not only is fluid mechanics used to minimize drag of a car, it is used to optimize the flow in the engine itself. And so in my research field, I study combustion. I didn't do car engines. This is just from a video I found online. But here they are studying, this here is the combustion chamber in your car engine, and they're studying how a flame grows from a spark on various levels of turbulence. And so here, and we'll learn what turbulence is later on, so turbulence is an important part of fluid mechanics, but you can see here the flame is, the flame kernel from the spark is basically growing outwards, and in this chamber here, it is much faster than it is in this chamber here. And so to make your car more efficient, they try to go for, engineers try to design the chamber for the configuration on the left. And they use computational fluid dynamics to basically understand the flow and things like that. And so in my own group, I study the combustion of multi-phase reactive flows. And so fluid mechanics is a necessary ingredient of that. And this here is a numerical simulation of what's called a rotating detonation engine. So this is for advanced propulsion. On the bottom here, we have an array of injectors that are injecting a mixture of hydrogen / oxygen. And basically, the hydrogen and oxygen gets injected into the sort of this region here where they ignite and burn. And this wave, and I'll let it loop through again, but this combustion wave, it's not a flame, it's called a detonation. And so this here is a detonation wave that basically travels around and around and around, and engineers actually make these devices. And why they're interested in intentionally triggering a detonation or an explosion instead of just having a flame is if you think back to your thermodynamics when you're comparing the Otto cycle to the diesel cycle, for a given energy input, the constant volume heat, a constant volume heat addition process was usually more efficient. Well, it turns out that a flame, like you saw in that car engine in the previous movie, is essentially constant pressure. Is that the heat release across a flame is actually constant pressure, whereas the heat release across a detonation, which you see here, is almost constant volume. So as long as you can build a device that can withstand repeated detonations of, say, hydrogen and oxygen, you will get a more efficient combustion process, and that is a very active research area in both propulsion and in power generation. And the theoretical efficiency gain could be about on the order of 5-10%, which would be huge. Would save millions and millions and millions of gallons of fossil fuels each year. And our group also studies multi-phase combustion. So here is a particular explosive configuration. I'll let it loop through again. Where in this configuration, we have a high explosive charge here, and it's surrounded by a shell of aluminum particles. And aluminum particles are extremely reactive, so what happens is this high explosive charge basically pushes out this layer of aluminum powder, disperses it into the air, where eventually the aluminum ignites and burns. And this has applications for both the military and also for explosion safety. Aluminum powder has caused a lot of dangerous explosive blasts in unwanted plants, such as in China. What is it, in 2000, I can't remember the exact year, 2012, 2013, there was a very, very large explosion at a Foxconn plant in China. And so these things, and so what our group studies is basically that. And the material that you will learn in this class is a foundational block to being able to understand these much more complex and much more practical design scenarios. But, you know, as the saying goes, you've got to learn to crawl before you can walk. So first we just got to go over the really nitty-gritty basics so you guys can build the knowledge necessary. And so now that's should hopefully explain why we use fluid mechanics. And now we need to define what a fluid is. So, oops.